Welcome, everyone. We are excited to have you here today for our Ask the Experts webinar on slope design analysis methods. We will get started in just a minute as we let a few more people in from the Zoom lobby. Thank you for those that are here for your patience while we do so. In the meantime, we'd love for you to say hello in the chat and let us know where you're joining us from. And while we wait, I'll take just a moment to introduce the Geotechnical Center of Excellence for anyone that may not be familiar. We are an industry-funded and member-led interdisciplinary center that is housed within the School of Mining and Mineral Resources here at the University of Arizona. Our focus is in collaborative and practical applications as we aim to bridge gaps within and between academia, industry, and various fields of study. We focus on research, education, and professional development to support safe and effective geotechnical practices in mining. This webinar is part of our Fundamentals of Open Pit Slope Design course. If you're interested in registering for this course, we'll have a new run of it starting in September of this year. We're getting towards the end of the current run, but one of my colleagues will be posting links to the registration form and potentially the flyer as well, so you can find out more about it. Otherwise, you can also go to mining.arizona.edu/GCE to see a listing of all of our courses. I mentioned that we are industry funded. We do that through a membership model, which includes the partners listed here. I just want to take a moment to sincerely thank all of these organizations for their continued support of the GCE. It's their commitment to our mission that allows us to offer educational programming like this and all of our professional development courses and associated webinars. I also just want to recognize the Large Open Pit project. This course is underwritten by the LOP project, which also led the development of the 2009 guidelines for open pit slope design textbook that our course is based on. That text is currently undergoing an update, also led by the LOP, and we are very grateful to them for their continued collaboration and support. All right, let's go ahead and get started. My name is Julia Potter, and I'm the director of the Geotechnical Center of Excellence, and I will be your moderator today. I'm joined by a fantastic team who will help me make the webinar run smoothly. We have Cheryl Bukowski here, who is our professional development program lead. Hello, Cheryl.
Thanks, Julia, and thanks everyone for being here.
We're also joined by James McNabb, who is a senior R&D engineer here with us at the GCE. Hello, James.
Hello, everybody. Thanks for being here.
And Allison Brucey, our program coordinator. Hello, Allison.
Hi, Julia. Hi, everybody. Thank you for being here.
Now I will introduce today's expert panel, starting with Scott Silwick. We're fortunate enough to be joined by one of our lead advisors for this course. Scott's in that role. Scott is also a vice president at Colin Nicholas. Hello, Scott.
Hey, everybody. We're all happy to be here.
We're also joined by Felicia Weir, Director and Principal Engineering Geologist at PSM in Australia. Felicia developed the rockfall module for this course and brings a wealth of technical expertise in this subject and others. Hello, Felicia.
Hi, everyone. Thanks for having me today, Julia.
Next up, we have Rob Pratt, who is president of Colin Nicholas. Rob developed the course module on assessing simple failure modes, benches. Welcome, Rob.
Hi, everyone. My pleasure.
We're also joined by Carl Lawrence, Chief Technical Officer at Equilibrium Mining. Carl contributed the module on numerical methods discontinuum, as well as several other modules in this course. Hello, Carl.
Hi, everyone. Glad to be here.
And today we also have Matthew King, who is Principal Geotechnical Engineer with Pateau Associates. Matthew created Introduction to Kinematic Analysis for this particular module and has contributed to the course in other ways as well. Welcome, Matthew.
Hi, happy to be here.
And finally, we have Joe Carvalho, who is a fellow in rock mechanics for WSP. He contributed the numerical methods continuum module. Hello, Joe.
Hello, everybody. Nice to be here. Thanks.
Welcome. Thank you, Joe. Okay, a few quick housekeeping notes before we begin. As attendees of the webinar, you are muted and your video is off. If you'd like to ask a question, please use the Q&A function on the Zoom control panel, which is typically at the bottom of your screen. You can submit these questions anonymously, and you're also welcome to upvote other questions using the thumbs up button in the Q&A window. This webinar is being recorded and will be made available on our course site as well as the GCE YouTube page within a couple days of the end of the webinar. And finally, please note that the views and opinions expressed by our panelists are their own and do not necessarily reflect those of the GCE or any affiliated organizations. All of this content is intended for educational purposes only and should not be considered a substitute for site-specific professional advice or analysis. Thank you all for joining us. We're going to kick off today's webinar with this question, which in order to get the conversation started, I'm going to point to Scott Silwick, our lead course advisor. The question is, what are the most notable recent advancements in slope design analysis, and what developments in this field excite you the most for the future? Again, we'll start with Scott, and then the rest of the panelists are welcome to chime in.
Hey, Julia. That's a pretty fun question, I think, to get us started. I've been doing this, I don't know, 18 years now. And so I guess if I look back to, what is being done differently now than from 18 years ago when I started, that I feel like has been a big advancement in helping how we do things and how we do our slope analysis. The biggest one that comes to mind first would be how we put anisotropy into our slope models. And for those that don't know, when I say anisotropy, what I mean is how we put planes of weakness or a weakness model for a specific direction of sliding into the rock mass. So this would be to account for something like rock joints or fault sets or something like that. And this is really important when we put these into our models, because you'll hear people say out there that there really haven't been very many pure rock mass slope failures. And I would say in my experience as well that is true, that 99% of the slope failures that I've seen when I go out to an open pit and do site tours and site visits, there's always usually some major structural component or some weakness or alteration component that goes along with the failure. So how we put this anisotropy into our model makes a big difference in the analysis. It makes a big difference in the factor of safety, and it makes a big difference in how we design the slope. So the two big advancements that I've seen there are, number one, when we run limit equilibrium analysis, we can now put in something called the anisotropic line. And what that is you draw a line into the model, and it can be any shape. And the anisotropy that you put in will basically follow that line throughout the model. So it's really, really nice for bedded deposits or deposits where you have a lithology model where everything is deformed, because now you can have your anisotropy follow that. And then for a numerical model, something that's happened in the last 15 years that wasn't possible before is now you can generate a DFN, which is a discrete fracture network. So basically all of the fractures, load that into the model, and then the model will just automatically mesh around those fractures, which is a really nice way to account for anisotropy or jointing in your model. And then what developments in this field excite you the most for the future? I would say improvements in the meshing tools that we use for our numerical models, such as RS2, RS3, or FLAC3D. One of the biggest hurdles when I started in this field was that creating good, accurate meshes for your model took a lot of work, perhaps more work than even running the model itself. In the last 15 years, those tools have improved a lot, and it seems like they're on the verge of improving even more, which I think will open the door to a lot more people being able to pick up and run these models more quickly, which is great for everyone. But I think that's it for me. I'll throw it out to the panel if anybody else wants to add anything.
I can pipe in a little bit here. One of the advances that was made not that long ago, recently, and part of that we can thank Carl Lawrence for it, is the use of the FN and limit equilibrium together to create a probability of failure map onto the slopes. So you take all the all the DFNs, generate all the blocks, look at which blocks are kinematically feasible, and then the factor safety is run on those blocks. And you can do this very quickly across very large slopes, the whole pit even, and create a heat map for zones that will have a higher frequency of blocks forming and failing, and very quickly identifying on your pit where you're going to have the most trouble. So that's been quite a good enhancement to all of our tools. I don't know if Carl wants to pipe in, since he was one of the architects of that. Carl?
Yeah, no, I think, Joe, that's definitely, the more use of DFN and more accurate representation of structure in our slope, which is similar to what Scott was harping on, right? That's really, most of the slopes we're seeing, they have structure at some level, and being able to include that probabilistically is even more advanced than what we do in at least a lot of numerical analysis now. I think the one thing that's, I don't know if we call it recent or not, but I think everybody on this call here probably started doing this type of work 20 plus years ago when, computers were not what they were at the time, and the scale of models, the availability of data just wasn't there. And now, working with mine sites, we're talking about terabytes of data that are available. So all of the ability to actually relate it back to true slope performance, as opposed to looking at purely theoretical or kinematic options. We're really getting to a phase where, our slope designs are really, tailored directly to the actual site specific data, and we can actually manage that data pretty readily in any of the models or any of the different design analysis tools that we choose.
Great answers thus far. Anybody else on the panel want to chip in on this question? All right, we have plenty of others. I think we'll go to another one that's kind of in the same vein of emerging technologies. I think I'll probably put this to Carl first, because I know this is an area of expertise of yours, Carl. Are there efforts to use AI or machine learning for failure back analysis purposes? It seems there could be a lot of value in throwing multiple data sets at an ML model to find potential contributing factors that aren't obvious.
Yes, I would say 100%. There's people working on this now at different scales. AI, and there's another module which I'm sure everybody has went through in this course as well. But it's being applied to everything from data collection through to the modeling aspects. Kinematics and things which are natively simpler, like there's always ability to do probabilistic analysis. But when we get into the more complex models, going into 2D, maybe limit equilibrium, and then into 3D, we can see it being used more now in 2D. That's largely because of the availability of computers to be able to run these tools. And then people are using surrogate models. So you'll see this term being thrown around, where we basically start to house all of these models together or run thousands or tens of thousands of models to try to train a machine learning model. And those are helpful, I would say, and they're good approaches and good applications of machine learning. The one thing just to be aware of is, your model will still only predict what you've trained it to look for. So it's not going to really look for the occurrence of a adversely oriented fault. All right, and that type of thing I haven't quite seen done yet, but I'm certainly open to hearing what the other panelists have to say as well. I haven't seen anything at a larger scale of 3D modeling looking to do back analysis.
Great, thank you, Carl. Anybody else on the panel want to have anything to share regarding this question? All right. We'll move on to a question for Rob, and that is RQD ever considered in catch bench design for rockfall? The idea being that lower RQD might lead to more rockfall and vice versa.
Yes, it's a great question. and I get the idea. There really are no very reliable relationships between the two, but I think the idea, the simple concept of a more fractured slope is more prone to rockfall is a pretty widely accepted idea. I think that's the essence, essentially, of the question. And I think when we think of weakened slopes, highly fractured slopes, there of course is the nature of the ground itself, as well as blast damage that contributes to rockfall in a dilated slope, which then leads to rockfall. So I think in the sense that the more highly fractured the ground, the more damaged it may be, however it comes about, whether it's the raw nature of the ground or through blasting or mining induced. It's an important point, and I think we spend a lot of time in trying to identify these contributors to rockfall and to try to mitigate it in whatever way we can. If we have mining practices that lead to more highly damaged rock, we do what we can on the blasting side to help reduce that to whatever extent we can. And if we have a particular rockfall problem in a particular area that might be associated with bad ground, it could possibly be due to some larger scale issue. Oftentimes, bad ground correlated to RQD could be correlated to rock structure. And in a larger scale problem, basically a slope that's gradually moving on you and that is causing a rockfall problem. And so in that sense, I would say it is the two are related in that sense.
All right. Thank you, Rob. Any other comments from the panel?
Yeah, I'll just add in that, like Rob said, yeah, RQD is not necessarily the top parameter we're worried about when we're doing a bench design, but it is something that I'll always worry about when we're considering different mining increments. So for instance, if a mine is considering going from single to double benching, and if they're using cable shovels, that would be from like a 15-meter bench to a 30-meter bench. At that point, one of the things we would always typically look at is, okay, well, what is the RQD? How fractured is the rock? Just because if you have 10 or 20% RQD or 0% RQD, even if it's hard interlocked rock, it may be okay to single bench that, but double benching it in that scenario is probably a bad idea. Once you start exceeding a 15-meter bench height, you probably need to start worrying about the rock mass quality a little bit, which is when RQD might potentially come into the picture.
Thanks, Scott. Joe, I think I saw you on mute. Go ahead.
Yeah, I was just going to say, I think there is an opportunity to find out where the RQD threshold is that will change the type of rockfall, basically from individual large blocks to more of a screed that fills in banks very quickly, benches. So I've seen in South America mines open pits where RQD is poor, very poor, below 10%, where you basically fill in all the benches and you end up with a continuous slope of screed. So it may be possible to actually kind of put a differentiator of what kind of catch bench mode you have to be on, whether it's just a continuous bunch of screed or trying to catch big rockfall.
Thanks, Joe. Go ahead, Felicia.
I think this is something that comes into, it's not just about the catch bench, it's about what batter face or bench face angle you're actually putting into that rock mass as well. If it's highly fractured and a low RQD, have you got the right bench face design? So it's a holistic design look, not just at your berm widths. And to remember that a few initial rock falls can indicate a larger failure might be coming. So
Great point.
I was just going to say, further to what Scott was mentioning about the double bench consideration, rather than just looking at the RQD, we'll actually look at the rock mass rating or the GSI parameter just to see what the overall quality of the rock is. And obviously being the more competent the rock, then likely the better chance of being able to actually successfully double bench.
Thank you, Matt, and everyone. Great discussion there. I think we will move on to another catch bench design question, which was originally asked of Felicia and Rob, but of course, as always, the rest of the panel is welcome to chime in. Maybe we can start with Felicia this time. Modified Ritchie criteria only considers bench height to determine bench width, but we know that bench face angle and features have a big impact on rockfall trajectories. Does this imply that the criteria is overly conservative for the design and therefore can work well with achieved slopes that don't meet the design? It's a big one. Go ahead.
Long one. All right, so the Ritchie criteria was originally developed by Ritchie after field trials for a very limited number of slope geometries for roads. So it wasn't specific to open pit mining. And then the modified Ritchie criterion came in when I think it was Colin Nickel modified it for a mining application. I think this comes back to that holistic look at the pit slope design. So it's not just berm widths, but you're also considering bench heights and batter face angles in one go. But the Ritchie formula is conservative, but it gives you a good rule of thumb that you can apply, for example, in a feasibility study when you don't have, or pre-feas when you don't have necessarily a lot of experience in that particular geology. It could then be something that you then actually review and look for slope steepening options, particularly once you've moved into operations and get some experience with that particular rock mass. Rob, what do you think?
Oh God, I've been excited for this question for a while. So this is a great one. I think whoever posted the question, I think you have some insight into, you've used the relationship before, you work with it, you looked at how it impacts your slope design. I think you've got some really good intuition about it. So, and I think that's all right on the money. Ultimately, the question is, what should our criteria be when it comes to bench scale design? And this modified Ritchie criteria, which Felicia explains the history behind it very well, is a tool for trying to achieve some criteria. So we know that the taller the slope, the wider the width we need to contain the rocks that fall from it. So that part is pretty intuitive, makes sense. So, but when you go to apply something so simplistic to a massive slope design, it seems overly simplified, and it seems like you're really selling it short, that we can do better. I think we all feel that way. So the key part when using the modified Ritchie criteria, or any criteria for that matter, is how you use it. And the way we like to use it is we like to set a target reliability of achieving that width. So ultimately, the criteria that we like to use is what target bench width do we want to hit? Do we think we need? And what is the reliability of achieving that target bench width? So if it's 0.2 times h plus 4.5 meters, which is the modified Ritchie relationship, how often do we have to hit that width? In some cases will be wider, in some cases will be narrower. I'll put I can't help it. I got to put a little photo or an image into the chat. I guess I can't do that. That's okay.
You should, if you want to send it to one of us, Rob, we could, if you're not able to put it in the chat, we should be able to.
Okay.
Just, yeah.
I'll send it
Email it to
you.
James.
Okay. But the point is that we can use a certain reliability of achieving this width as a metric towards a reasonable criteria for bench scale design. And the nice thing about the reliability component is it allows us to address the issue that we talked about just a minute ago in the previous question about the condition of the ground and the how fractured it is and how blast damaged it may be. And if we think we're going to have those kinds of problems, then we can go more restrictive on the reliability. Whereas if we have, let's say, a mine where we have good history of blasting practices, pre-splitting and such, which is not an easy thing to do for for a mine site. You need specialized drilling, you need good drillers, there's a lot of technical details involved there. And oftentimes it takes a long time to get to the point where an operation can really dial in their blasting. But if you know that you've got that to your advantage, you've got some history, then you can ease up on the reliability part. And so that's where the engineer can use this criteria in a way that is sensible and appropriate for whatever site they're working with.
All right, thank you, Rob and Felicia. Did anybody else want to chime in on this topic before we move on?
Yeah, the last question in there was, does this imply that the criteria is overly conservative for the design? So I want to hear Rob and Felicia's answer on that.
It certainly can be. If you expect that, if you use that criteria and insist that you have to achieve that with 100% of the time, that's the reliability part, then yes, I think you would be certainly overly conservative. If you dial that back and said maybe a lower reliability, whatever it might be, 50, 60%, you're achieving that criteria, then in that case, it wouldn't be so conservative. And Carl spoke about, the advent in technology about for reconciling, doing reconciliations and measuring the achieved configurations. It's nice to be able to measure what you actually mined and then compare that to this criteria to see, well, what does it mean to have 80% have mine basically have a mine with a slope with your catch benches achieving this with 80% of the time. What is the physical implication of that? What do the miners think of that slope, and how safe do the miners feel working below that slope? So that might be an open-ended answer, but I think maybe the short answer is that yes, it can be very overly conservative, but also if you dial back the reliability, then it may be more appropriately conservative.
I agree with Rob that yes, it can be quite conservative for the design. And I think that's why we now go to, other options like doing our rockfall modeling and trying to understand what are actual appropriate berm widths to manage the risks that a specific site faces. And as Rob talked about already, all of those technologies that exist for helping us actually look at what the design was versus what was being safely achieved.
Thank you both, and thank you, Scott, for ensuring we wholly answered the question. I think now
I was just curious.
No, I appreciate it. We'll turn to a couple of live submitted questions submitted by the audience on a topic that we touched on briefly previously. I think we'll start with how sensitive are stability analyses involving DFN models to fracture lengths? It seems like it could have a massive effect, and I've always considered length to be one of the more difficult things to measure confidently. Does anyone want to get us started on this one?
I can just start piping. I don't think you can divorce length from spacing. So yeah, you got to take it in conjunction, because you do need, length, spacing, number of sets that you're considering. So definitely the longer your fractures, the more opportunity to create individual blocks. That's a given. But I think you'd have to be careful that you need to consider with spacing, especially if spacings are very different. You can end up with blocks that are very long, very narrow. In the extreme, you have sedimentary rock with cross fractures, and you end up with slabs instead of blocks. So all that really has a great effect on the stability and how the analysis behaves.
Thanks, Joe. Alicia, I see you've unmuted. Go ahead.
Yeah, and I agree with the person asking the question. Length is 100% one of the most difficult factors in a structure model to determine accurately, particularly if all you've got boreholes. Then all you can do is have a good engineering geology best guess, if you like, and I'd encourage you to undertake sensitivity analyses on varying the lengths in your DFN models, would be how I'd look. And they're always going to be sensitive to length, and as Joe's pointed out, spacing and orientations. But if you can keep the others consistent, vary your lengths, and look at that sensitivity, it'll help you understand potential implications for the stability.
I would even add to that, in addition to the length, you need to consider rock bridge size. They go hand in hand. So typically when we introduce jointing into a model, we introduce the persistence. We try to give a ratio of fracture length to bridge, because the bridges control the strength. So yeah, all of that, it's purely a geometric consideration, but it's a very important one.
Yeah, just adding to what Joe says, like when we're talking about rock bridge and the lengths, it's about scale, right? If we're doing bench scale analysis and things like that, and we have 10-meter long fractures, then yeah, it's gonna make a difference. But once we get the overall scale, what's the spacing? How does that relate to the length as well? And that's where we try to use rock bridge and to try to quantify that a bit, whether it's in discontinuum or continuum based models.
Just try to address the very end of the question. Agree with everything everyone's said so far. And also that it is one of the more difficult things to measure confidently. One big way that things have improved in the last 10 years as far as measuring lengths go is drone surveys and remote surveys using point cloud data. Just we're able to cover a lot more ground with a lot better lighting conditions to get those measurements. And then the way that we usually measure length of joint sets here is rather than try to measure the total length of all the structures, a lot of times it's quicker to use window mapping. So basically break up the good exposures you have in different windows. And then if in each of those windows you can measure how many of the structures there are, and then what the longest one of those structures is, you can usually safely assume that the lengths follow an exponential distribution. And if you have those data points, then you can calculate what the mean length would be from that data. But that's a quick way to gather a lot of length data from a point cloud survey, or if you're in the field, from some field reconnaissance mapping.
All right, thank you, everyone. I think we'll move to another live question on DFN models. And in case we haven't already said it, for anybody that's not familiar, DFN stands for discrete fracture network models. I think we may have said it previously, but just want to cover that just in case if you're not in the course or you haven't gotten that far yet. This question is again for the panel. Is there any success in DFN conditioning based on borehole versus window mapping generated DFN models? What do you think about conditioning integration, even using seismic data with DFN models?
I can comment from a recent batter optimization study we were doing, where we had DFNs that were conditioned based on boreholes. And when we compared that to actual exposures in the rock mass, we found that the DFN had much higher fractures and fracture intensity than if you were basing it on just window mapping or an assessment of the batter face. And a lot of that, I think, loops back to the previous question about length. And in the boreholes, we're going to take every single structure that we've encountered, but if you were mapping them, they might be quite short and you wouldn't necessarily consider them. And so what we did in that example was actually have to factor down our P10 or our intensities from the boreholes to better match the fracture intensity that we actually encountered. So if we'd gone with just the borehole DFN conditioning, we would have really penalized the batter face geometry. So I'll leave someone else to answer the second part of the question on the seismic data.
Thanks, Felicia. Does anyone feel comfortable taking on that second part of the question related to seismic data? Scott, I see you've unmuted.
I don't know if I feel comfortable with that, but I was just going to say that we found the exact same thing as what Felicia said with some of the studies we've done, is that if we go backwards from our window mapping to our borehole data, and then look at the DFN from that, that we always see smaller block sizes generated from the borehole data than we do from the window mapping. And it's interesting because when we do the bench analysis, in general, the window mapping data seems to calibrate better to the actual performance in the pit than the borehole data as well. So there are some disconnects there. They don't always equal each other. But I'll leave it to someone else to talk about the seismic data.
I'd say it's an interesting idea, the use of the seismic data to help condition the DFN model. But I think you have to be very careful in taking it this far. I think the difficulty in all the variables that go into constructing a DFN, as discussed, addressing the first part of the question, to a certain extent precludes going too far with these models. In other words, if you pile assumption on top of assumption, you get to the point where you lose confidence in your model. So, and I think taking the step of conditioning the seismic data, I think it would be very difficult, or at least I haven't seen anything like that. And there's any thoughts on how that might be done, I think that might be curious, but you'd have to do so with great caution.
All right. Thanks, everybody. We've just about covered that one. I'm going to move now to a slightly bigger picture question that I think many of you would likely be able to answer, but maybe we'll start this one off with Joe, if you're willing, Joe. In the context of open pit slope design, how do you approach the selection and application of different slope analysis methods? For example, limit equilibrium analysis, numerical modeling, probabilistic analysis, to ensure both safety and economic viability. Specifically, what criteria or guidelines do you use to determine which method is most suitable for a given scenario? And how do you balance the trade-offs between accuracy, computational effort, and practical implementation in real-world projects?
Okay, that's a mouthful. So
yes,
I've always believed that you walk before you run. So I think you start simple. It really depends a lot on the available data. No point in going into a very complex model without the proper data to feed the model. in terms of, yeah, I would say you'd start with a limit equilibrium analysis, as it was said here today. They have advanced to the point where you can actually include quite a bit of anisotropy and other, niceties that we didn't used to have in the early days. And then you can move on to numerical modeling. One of the things that we usually do to confirm the results from limit equilibrium is that the numerical modeling is going to give you a more accurate or true failure surface, which you might miss in the limit equilibrium depending on the search method. So it's always a good way to check back on that. And when you talk about probabilistic analysis, it's still quite a little bit prohibitive in numerical modeling, especially in 3D. It's totally available in limit equilibrium analysis. So it's interesting that even today, designs are based on limit equilibrium analysis, where numerical modeling is much more used for back analysis and confirmation of things. So yeah, there's no silver bullet here for a specific method. I would just say you'd start simple, gain knowledge, and depending on the data available, you just increasing the complexity of your model. That's kind of the way to go. Yeah, real world constraints like time frames, and some of these models take, large bit models take weeks to run, like days. It's a lot faster these days, but we used to wait a week for a single model before you could try, another combination of parameters. So yeah, it's like I said, start simple, try to understand which factors, which parameters are really influencing your model, and then move on to the more complex.
Thank you, Joe. Did anybody else want to chime in on this topic?
Yeah, I'd agree with Joe. It comes down to more so for me the stage of the program. Like if we're order of magnitude or pre-fees, we're not running 3D discontinuum models. We're running kinematics and maybe limit equilibrium. As we get more into feasibility and execution level, then we're getting more into the more numerical modeling or more sophisticated type tools. In terms of choosing one, I often get that question as to, which one do you choose if you're in execution level? Like, what are we going to choose? And I think it really comes down to, what's driving the slope design. Is it bench scale kinematics? It doesn't make sense to run like an overall scale, like big 3D numerical model if your only challenge is like rockfall and bench design. So it comes down to what's driving the underlying mechanisms and what's driving the design in terms of choosing between these. That said, I think everybody would sort of agree that there's some level of standard in the industry, partly based upon guidelines and what sort of has driven this course. There's a certain acceptable standard that once we get into execution level, I would say most operations and review boards expect some level of numerical analysis to be conducted for the design.
Yep, I think balancing time, budget, level of study, standard of care, all of those things, along with all the technical stew of factors that go into what is going to control the slope design, is just as much of a factor as anything. And this can be the hard part, is where the practitioner has to decide what really should the standard of care be for the project, given all those things, and then decide what should the analysis method be. So if it's, say, a large feasibility study for a big open pit with lots of faults controlling stability, that scenario probably lends itself to a big finite difference model. And time and cost, of course, notwithstanding. So in that sense, in that kind of situation, the practitioner acknowledges the risk, acknowledges the scale of the project, and works with the client to come up with a plan to put the best use the best analytical tool to analyze the most challenging problem to give the best possible answer for the project.
Thanks, Rob. Great answers all. Felicia, I saw you unmute earlier.
I was just going to support what Carl and Joe had said, and essentially a little bit on what Rob said too, in terms of it depends on the scale of the project and the life of the mine that's being proposed as well. If you're dealing with a 60-meter deep, short, 1 or 2 year project versus hundreds of or a kilometer deep pit with interaction with existing underground, things like that, they're all very different. And so you have to think about what's controlling your slope design and what is the life of the mine and the scale of the project that you're looking at.
Yeah, I was just going to add it can depend on the scenario of what's going on. We've had examples where there was a instability on a slope, so I can give you an S-wedge answer today, but then to give you an answer by the end of the week, doing something in 2D or 3D, like slide 2D or 3D, some kind of analysis like that where it's limited equilibrium, it takes a little longer. But if you want a numerical model to answer how exactly this instability evolved and developed, that's what takes those days and weeks of computer runtimes to analyze, and that you're looking at months of analyses, as everyone was alluding to. So yeah, it does end up being fairly specific to, well, what's the problem, and then you can pick the tool appropriate to the problem.
One keyword I haven't heard yet is the geology model. When I think, how do you approach the selection of slope analysis method? It's like, okay, well, definitely want to take a good hard look at the geology model. What's the geology doing? What's the structure doing? How does that interact with the pit design that's been proposed? Just from that, you should be able to conceptualize what types of failure mechanisms could we have. And then you want to make sure you pick a tool that can analyze that failure mechanism properly, because not every tool can analyze every different failure mechanism. And I'm definitely in 100% agreement with everyone else that once you've gotten that far, you don't want to pick the most complicated tool in the world, because you're going to have so many variables, so many sensitivities that you might lose sight of what the model's actually doing. So once you get to that stage, then, pick as advanced of a tool that you need to model those failure mechanisms that you think you might be at risk for with a particular design.
Yeah,
The other thing, Scott, was to remember that every tool and analysis method has limitations. And so it's keeping that in mind. No matter how complicated and fancy a model you might have adopted, there's still going to be limitations with it. And you just need to be aware of those when you're doing your design.
Yeah, I was just going to reinforce Scott's first sentence. There's no geotechnical model without a geological model. So everybody listening here, get your geology in order first.
The last part of that question just mentions practical implementation in the real world. And I think that's the part that stands out to me, just because, when somebody comes to us and asks us to run these different types of models, the first thing we ask is like, well, how's your current slope performing? Because that's the best model you have. It's real life, and it's actually what you've been through. So like whatever's happened on that slope, unless you're going to go into a different geology or geotechnical domain, you've largely lived through it. So that's what we would use to really choose the path forward. It's like what you're seeing in the current slopes, what's typically governing in your area.
Great. I think that was a great collaboratively answered question. Thank you all. Great discussion there. I think we'll move next to another live question. We'll go back to bench design for this one. This was specifically directed at Felicia. In your course presentation, I recall you mentioning that 3D rockfall modeling seems to have a large lateral spread. Do you know why this might be, and does it seem unrealistic to you?
Oh, good question. All right, so 3D rockfall modeling, I showed some examples of different software packages, and that they all showed quite a lateral spread compared to what the field trials had found. So instead of saying, is it unrealistic? I think what you've got to say is that it's low likelihood that they would actually spread as far as they had in that example. What I think and that's actually indicated in the colors in some of the figures I showed, that while the 3D rockfall modeling showed it was possible that a rock could spread that or fall in those locations, the percentage of rock falls that did was actually very low, often half or 1%. And so I think what it's doing is simply indicating to you that it's a low likelihood where it's possible to spread. I think it's just why this might be. I think it's just a reflection of probability and the computation in the software. One thing to keep in mind with the 3D rockfall modeling as well is that it's actually highly sensitive to the slope geometry that you're putting in. And if you put in a smooth design surface that has no roughness, you'll get quite different results compared to if you put in an as-built. And if you're doing a design cutback and you put in a smooth surface, the 3D, a lot of the 3D rockfall modeling doesn't then account for surface roughness. So just be very careful. It's something we've had to start building in roughness into some of the 3D surfaces that we're analyzing.
That's a great point. We have a grad student doing research on this very topic, and we found the same, Felicia. So I'm glad this question came up. Did anybody else have anything to add for this one?
I think it's a great opportunity to conduct a lot of rockfall trials in the field, like send those 1,000 rocks over to actually show that it does or does not spread the way the model says.
Everyone loves a rockfall trial.
It's a
except
great
for
opportunity.
production.
We have some synthetic rocks headed our way to do just that, so we're pretty excited. All right. Thanks, Felicia and Matt, for that one. I think we've got time for one more question. I'll go to another pre-submitted one. When using as-built slope data to inform a pushback design, and there are plans to improve mining and blasting methods for the pushback, does your design reflect potential improvements, for example, steepening, or does it reflect the current slope with the understanding that steepening could occur? Essentially, they're asking, would you advise that you underpromise and overdeliver versus overpromising and underdelivering when it comes to planned improvements on your blasting and mining methods for future pushbacks?
We're getting pretty heavy with these questions now. Oh man. Yeah, I think once again, an excellent question. And somebody has been through some battles before and knows the drill. This is a difficult dilemma. I think ultimately, as the responsible engineer, you have an ethical responsibility to make sure that what you recommend to any client at any site in any part of the world meets a reasonable standard of care. So, and in this scenario, there's a difference between saying you're going to do it and actually doing it, and not to say that not to make out any company or any mining group as having nefarious and misleading kind of intentions, but achieving best practices is not easy, and there's so many things that get in the way of achieving best practices. So I think in this kind of a situation, if you were going to make the plunge and recommend some call it an optimized design, assuming best practices mining, then I think you would need some evidence of that before you went out on a limb and made that kind of a recommendation. A trial mining is always a good thing to do. Maybe some experience. Maybe you have an operations crew that comes from another site where the company can borrow experience from another site. That can be very powerful. I think I personally would approach this dilemma with digging deep and trying to decide for myself what I thought is the most ethically responsible answer that does not overpromise. Something that is realistic based on what I've seen, what I think that the company is capable of, etc.
I've been on a mine site where the mine planner will open up your design report and simply copy out the table, and then they close the report. And so they didn't, you could only achieve this design if you're going to put in horizontal drain holes and do X, Y, Z. And so if you're going to recommend a steeper design, you have to be very clear on what goes hand in hand with that in terms of operational constraints. And I'd consider establishing hold points where they can't continue progressing until they've verified that the operational constraints and that the design is being achieved. And I would clearly state what the consequence of not achieving that would be. So what does slope flattening look like, and what's the cost? And putting things in terms of cost to the management can be very helpful. So it's going to cost us this much to put in improved blasting and put in horizontal drain holes versus the flatter slope design. But I highly recommend some hold points to where you've got opportunity to review how the slope performance is going.
Yeah, I would say as well that typically you've got more than one department in a mine that is responsible for the success of the whole operation. So they all have to be in tune, and they all have to be meeting, the requirements or what was assumed in the design. Because if only one of them fails, you may be jeopardizing the whole design. So communication as well.
I think it's what everyone sort of said, it's about risk, right? Like even when we make a recommendation, it's subject to certain assumptions, and making sure everybody's aware of the assumptions and the risk associated with that. Even the mine planners, because we don't want to implement the design that we're backing ourselves in the corner, that we don't have any contingency there to sort of react to something that might change. So as long as we can collaborate with operators, with other parties, and understand the risk, I don't look at it as under or over promising. We're just trying to get through and get the most efficient and safe and most economical design that we can.
Yeah,
Just to add to that, I don't think you want to consistently under promise to a great extent. I don't think the stakeholders would be very happy. So you don't want to be a cavalier, but you do have to be careful. And I agree with Rob. I'd rather be on the under promising side rather than the over promising, but trying to get as close to the line as possible.
Yeah, I was going to say a good word that Carl raised there was contingency. And I've been through this a number of times where we give the client two designs and you say, here is your base design that's achievable. But then here's the carrot of it, as Felicia was saying, if you do all these best practice things and you can demonstrate that you can achieve them, then you could steepen the design by up to, 4 degrees or more. because mine planners love to steepen designs, but they really do not like to flatten, because now all of a sudden people are looking at it as, well, that's a loss. You're leaving ore behind and whatnot. So if instead you give them, well, here's your base slope that is a design that you expect is achievable, then anything that they can do better than that is a bonus. And it's the type of thing of, if you're operating on your steeper design, and as Carl mentioned, you suddenly hit a surprise and things aren't going well, you can then always take a step in and go back to your original design and continue from there.
Great. Thank you all. Scott, go ahead. I think we've got time for one more comment.
Yeah, I can be quick. Just when I read this question, one of the first questions that came to my mind is that I would ask in this situation would be, get with the geology department and with the mine planning department and say, okay, for this pushback, how is the ore distributed throughout the pushback? Because that will change how you'd approach this problem significantly. For instance, if the ore was concentrated, very heavily at the bottom of the pit, there was just one seam or one bed down there that had all the ore, you'd probably want to be more conservative in your approach to this question, just because if you have a lot of bench failures and you have rockfall issues and end up needing to take a step out, it's like you might lose half your ore from that step out at the bottom of the pit. And it might be a pretty bad situation. Whereas some deposits, like porphyry deposits, the ore is more evenly distributed throughout the whole pushback. And in that case, it would be the more type of situation where it's like, okay, well, if 2/3 of the way down the slope, we have to take a step out, the economics don't change too much. So in this case, we might want to be more aggressive. But considering that distribution of ore and how that works into the mine plan is something to think about with this question too.
Great. Thank you, Scott. And thank you all for your excellent comments. We are out of time. I will just note that this is one of several courses within the GCE arsenal. And we do have 2 that are opening on June 10th, water and mine operations and slope stability, as well as structural geology for geotechnical professionals. We're actively working on geotechnical considerations for blasting and mining. So please stay tuned for that. I saw a question come in about blast damage. That was excellent. If you are enrolled in the course and we didn't get to your question, I know there was a couple, please be sure to put that on the discussion board and we'll direct our panelists or appropriate course contributors to get that answered for you. And last but not least, I just want to thank our panelists for being here today and so generously answering all of these questions, and to our participants for asking such excellent questions. Thank you all, and I hope you have a great rest of your day.
Thank you.
Thanks, Julia. Thank you,
Everybody.
everyone.
Thanks, Julia.
Thank you,
Thanks, everyone.
GC.
Thanks, everyone.